is 2 constant volume and 2 isentropic, whereas Stirling cycle 2 constant volume and 2 isothermal. Breton cycle 2 constant pressure and 2 isentropic. Ericsson cycle constant pressure and 2 isothermal. And Carnot cycle is consist of 2 isothermal and 2 isentropic. So this is generation in case of Stirling cycle and Ericsson cycle. Regeneration is the heat recovery. In that case, the efficiency of Carnot is same as efficiency of Stirling, is same as efficiency of Ericsson. Cycle we will consider a PV graph. We have a cylinder. This volume is called as clearance volume, and the remaining volume is called as stroke volume, which is given by pi by 4 diameter of multiplied by stroke length. We have an inlet wall, we have an exit wall. This one is called as top dead center. This one is called as bottom dead center. So during the starting, we have the piston at this position. So the stroke will start from this point. Initially, this is filled with air plus fuel mixture at atmospheric condition. That equals to P1. As the piston will move to the left hand side, the air will be get compressed, and this compression process will continue till we attain a point equals to 2. So 1 to 2 is called as 1 to 2 is isentropic compression. At the end of the compression, the piston will reach the volume at the end of the compression to the volume at the end of the suction is represented by V1, and this is represented by V2. V1 is equals to Vs plus V2 is called as V2 equals to clearance volume. This is at the end of compression. 1 to 2 is called as compression process. So we define first ratio called as R is compression ratio. As the name indicate, compression. So this is defined on compression process from 1 to 2. And remember, ratio is always greater than 1. Therefore, compression ratio is given by V1 divided by V2. In Otto cycle, that is petrol engine, this is roughly 6 to 10. Upper limit is limited due to knocking tendency. Then at point number 2, the heat is added at constant volume, assuming that the piston is held constant, which is practically not possible. So 2 to 3 is a constant volume heat addition process. As the heat is added, the pressure will reach to the maximum value equals to Pmax, and Pmax equals to P3. The pressure attained at the end of compression is according to the ratio 6 to 10. And at this point 2, that is at point 3, the temperature is max. From 3 to 4, we have a isentropic expansion. In that case, the piston will move from PDC to PDC, executing a power stroke. So from this, it will expand like this up to point 4. Again, the piston will reach to BDC and the exhaust gases are expelled. This process is called as expansion process. This one is constant volume process, that is the heat rejection. This is the constant volume heat addition. So we define the second ratio, which is normally represented by RE. It's called expansion ratio. Expansion ratio is always greater than 1. So V4 is more than V3. So this ratio is V4 by V3. So there are only two ratios. One is called as compression and one is called as expansion. But if you observe the RE, which is basically equals to what? V4 by V3. But if you observe the PV diagram, V4 is same as V1, V3 is same as V2. So this one is V4 is same as V1, V3 is same as V2. So this is same as R. So there is actually only one ratio, that is called as compression ratio or expansion ratio, and both are equals to RE. Here 1 to 2 is isentropic process, and for isentropic process we have T2 by T1 is V1 by V2. There is an inverse relation between temperature and to the power gamma minus 1. That is R to the power gamma minus 1. And secondly, we have 3 to 4 process, which is again an isentropic process. T3 by T4 equals to T3 by T4 is same as V4 by V3 to the power gamma minus 1. This is same as RE to the power gamma minus 1, but RE is same as R to the power gamma minus 1. So if I say this is equation 1 and this is equation 2, the right hand side of both equations are same. So T2 by T1 is same as T3 by T4. The heat is added at constant volume, that is 2 to 3 process. This is Q in. So Q in is defined as constant volume process. So is CV, higher temperature is T3, lower temperature is T2. Heat is rejected during 1 to 4 process. So this is Q out equals to, is also constant volume process is CV T4 minus T1. This is a cyclic process, so we can write cyclic integral del Q equal to cyclic integral. So W net is same as Q in minus Q out. According to second law, the thermal efficiency or air standard efficiency of Otto cycle is given by W net divided by Q in. W net is Q in minus Q out divided by Q in is 1 minus Q out by Q in. Q out is CV into T4 minus T1 and Q in is CV into T3 minus T2. So CV will be cancelled. It is 1 minus T1 upon T3 minus T2. To solve this equation, we have this condition T3 by T4. So we can make it equals to T4 by T1 is equals to T3 by T1. So subtract 1. So we get T4 by T1 minus 1 equals to T3 by minus T1 by T2. So we obtain this term here, that is T4 minus T1 by T3 minus T2 is same as T1 by T2. So put this value back into this equation. So the efficiency of T1 by T2 in simplest form. So if you know the temperature before the compression and if you know the temperature after the compression, we can evaluate the efficiency. So that means that if you know only the compression ratio, we can find out the air standard efficiency of Otto cycle. T1 by T2 is, you can obtain from this one. T2 by T1 is what? R to the power gamma minus 1. So this equation is 1 minus 1 upon R to the power gamma minus W net divided by Q in. If you know W net and Q in, you can calculate it, and even you know the compression ratio, you can calculate it, and even you know the temperature at the start of compression and the end of compression, you can calculate it. Another equation can also be written as T1 by T2 is same as T3 by T4. So as 1 minus T4 by T3, because these ratios are same. T2 by T1 is same as T3 by T4. So we have same proportion here. So when the compression ratio is 1, efficiency is also equals to 0. 1, this is R is 1, so efficiency equals to 0. It increases like this, and does it now become flatter and flatter, and finally it is almost constant. Where it is constant is probably the range from what? 6 to 10. So there is a very marginal increase from 6 to 10. So any working range is from 6 to 10. At 10, working range for petrol engine is taken as 6 to 10. Response is very good up to 6. Knocking tendency. Instead of diatomic gas, if we use monatomic gas, your curve will deviate from this. Monatomic gas. And for actual, that is for polytropic, we have this one is gamma equals to 1.33. Net work done in the cycle is represented by the area enclosed 1, 2, 3, 4. That is this hatch area. That is, if we have modeled this area is something like this, whose base is equals to what? Vs. The height will be called as Pm. Diagram. This one is called as actual indicated diagram. What is the advantage of this diagram is that it is assumed the pressure and expansion remains constant. It's called as indicated mean effective pressure. So you have to equate this area, that equals to this area is a rectangle area, is Pm multiplied by Vs. If we equate this area with this area, that is the actual W net, then we can solve for Pm, and that is called as indicated mean effective hypothetical pressure, which is assumed to be constant over the entire stroke. That this is capital W. This is a capital Vs, then it's capital W, joule and joule. If we work out the specific quantity, we will get Pm. So what is Vs? Vs is basically V1 minus V2. Vs is this volume, that is V1 minus V2 is equals to W net. W net is given by M multiplied by specific work, that is W net. So we can find out Pm as W net divided by multiplied by mass divided by V1 minus V2. But this is, or otherwise you can also write this as capital W net divided by V1 minus V2. You can write this as W net volume divided by mass. Is it become a specific volume? And this volume divided by mass is also equals to specific volume. Characteristic gas equation, that is PV equals to RT P1 V1 RT1. So we can find out V1 very quickly using RT1 by P1. And we know the compression ratio is defined as V1 by V2. V1 by V2 is same as mass multiplied by V1 upon mass multiplied by V2. So it's same as V1 by V2. So we can calculate specific volume from V1 by dividing R. So in either we have to calculate Pm using this equation, or you can calculate Pm using this equation. In both cases, the answer will come in Pascal if the work is in joules per kg, specific volume in meter cube per kg, this total work in joules, and the volume in meter cube. Then later on you can convert into bar. Higher the value of mean effective pressure, more powerful will be the engine. So engines are basically just compared with PM, not with displacement. So 2000 cc engine is more powerful if mean effective pressure is 8 bar as compared to the mean effective pressure of 7.7 bar, because it clearly indicates that the area under 8 bar is more as compared to 7.7 bar. In every cycle we generate more work. So some quick facts about the Otto cycle and diesel cycle. The lowest pressure is P1, pressure is P3, highest temperature is T3, lowest temperature is T1. Point 1 represents start of compression, point 2 represents end of compression, start of heat addition, point 3 represents the heat addition, 3 to 4 is called as power stroke or called as expansion, and 4 to 1 is called as heat rejection at constant volume. The actual cycle will deviate from this because it is impossible to hold the piston at constant volume. We have holded the piston constant here, is it correct, for temporary, but the piston will move again. So the heat addition will start somewhere before the heat addition end of compression, and then it continue like this, and again the piston is hold constant. So this is called as actual indicated diagram. This portion is slightly deviated from the theoretical one, 1, 2, 3, 4. So it will be starting from 1, then goes along this, then make curve, and then like this. In addition to this, we have a loop here for suction stroke and exhaust stroke. So work done during the compression, suction and exhaust are entirely neglected. So this work is not considered. This one is actual PV. Step number 1 is Vs you are able to calculate if you are known the data pi by 4 d square L. Vc is called as clearance volume, is normally provided to you. And Vc is known. Your first job is to calculate V1, that is Vs plus Vc. Know V1 and you know Vc, then you can calculate R, which is called as compression ratio, and which is basically is defined on compression process. Higher volume is V1, lower volume is V2. The name compression and expansion is given based on process. This is compression, so it is called as compression process. This is expansion, it is called as expansion process. And to remember this, the ratio is always know this. We can calculate efficiency as 1 minus 1 upon R to the power gamma minus 1. And this efficiency is equals to W net divided by Q in. The process 1 to 2 is isentropic process, which follows the law PV to the power gamma equals to constant. So using this law, P1 V1 to the power gamma equals to P2 V2 to the power gamma. So we can very quickly calculate P2 as P1 into V1 by V2 to the power gamma. But V1 by V2 is called as compression ratio. So this is P1 into R to the power gamma. So you know the pressure at the end of compression. Similarly, we know the value of T2. T2 by T1, or T2 is always equals to T1 into R to the power gamma minus 1. So you can use this process only for isentropic. But when you are moving from 2 to 3, you can't use this equation. But we can still use the ideal gas equation, that is P2 V2 by T2 is equals to P3 V3 by T3. Ideal gas equation you can use for any process, but PV to the power gamma you are only allowed to use for isentropic process. Here V2 is same as V3, so this term is cancelled out. So using this, one of the term can be find out. Either P3 can be find out or either T3 can be find out. So one value he has to supply. Either maximum temperature he has to supply or the maximum pressure he has to supply. Once you know this, then you can go to 3 to 4. 3 to 4, you have to repeat this job. That is P3 V3 to the power gamma equals to P4 V4 to the power gamma. From this we can calculate P4 as P3. V3 by V4 is 1 by RE, and RE is same as R. Similarly, we can calculate T4 equals to T1 is 1 by RE to the power gamma minus 1. Remember, T3 is more as compared to T4, so that is why it is 1 by RE. And T2 is more than T1, so this is R to the power. R and gamma, they are same quantity. So these are the end conditions you can find out. So all state points you can find out, that is 3 state point for this, 3 for this, 3 for this, and 3 for this. 12 state points you can find out. If you know the mass applied, then you can use the ideal gas equation for first point. P1 V1 equals to mR T1. And you can apply this for all 4 stages. Once we know mass, can we calculate total quantity of Qin? Qin is constant volume process, is basically 2 to 3, which is the constant volume process. And this one is from 2 to 3, so this one is Qin. So this is T3 minus T2. Answer will be in joules if you use CV in joules. the Q out is from this process 4 to 1 is M is again a constant volume process. So this is T4 minus T1 and Q in minus Q out is W net. So Q in minus Q out. Follow the very simple steps. Once we know the Q net, we have a formula that is PM multiplied by Vs equals to W net. And very well find out mean effective pressure. That is W net divided by Vs. Value is given, we can use that value. Here is the entropy change from 2 to 3 process is same as 4 to 1 process, delta Ts. So if we know delta Ts and suppose it gives you value of delta S 23, is delta S 23 is basically equals to del Q 23 divided by T, integral of this. And is this process is a constant volume process. So we can write delta S 23 equals to M, and it's a case of ideal gas. So I can, this is CV. So delta S 23 into CV into ln is from 2 to 3. So relation for m dot fuel into calorific value, is it the heat supplied in actual practice? So how much fuel shall I supply to produce 1 kilowatt of power? How much fuel shall I supply to produce 1 kilowatt of power? That will be called as SFC. So SFC here will be defined as mass of fuel consumed multiplied by 3600, that is the conversion factor from kg per second to hour, kg per hour, divided by power produced. And the power produced is basically brake power. So it is normally called as BSFC. C always means BSFC. By default, engine is meant for brake power. Engine is never meant for indicate power. You have to say indicate power. But if you say power, it is always assumed that brake power. No additional work required for brake power. But if I have to say indicate power, then I have to use indicate power. So if I write BSFC or I write SFC is one and same. Unit is kg per kilowatt hour. The basic unit of m dot f is kg per second. M dot f is kg per second. 600 is the conversion factor and brake power is in kilowatt. Now unit you have to match. If you want to find out ISFC, indicated specific fuel consumption is defined as mass of fuel into 3600. This time is divided by indicate power. Just like BSFC and SFC, they are identical terms. PM stands for indicated mean effective pressure, or people number of times called as only mean effective pressure. This PM multiplied by Vs is called as W net. This is the work done in one cycle. So W net is PM multiplied by Vs. If the engine, and otherwise this equation can also be written as T into what? Omega. What is into Vs into N divided by 60. What is so PM? Vs is what? Vs is actually the area. Vs is this one, is the area of the cylinder multiplied by stroke length. So if I write A for area of cylinder, L for stroke, is it PMA ln by 60. Now this is a very common use formula and is represented by plan, PLAN by 60. Is PM is mean effective pressure. Similar to this, we can define BP, where the formula will remain same, PLAN by 60. But this one is called as PMB. What is PMB? Is brake mean effective pressure. P, which is by default is P, I base PM I multiplied by L multiplied by A multiplied by N divided by 60 power. The power produced by one cylinder. If we have multi-cylinder, we should multiply each term by n number of cylinder. Then it really matters the engine is 4-stroke or 2-stroke. So I write multiplied by small n. This small n represents number of effective cycles, number of effective power stroke per cycle. For 4-stroke, this value is equals to 1 by 2. After every 2 revolutions, you are getting 1 power stroke. And for 2-stroke, for every 1 revolution, we have 1 power stroke. Now this becomes the universal formula. Number of cylinder multiplied by plant multiplied by small n. Now it will solve all cases. A single cylinder, multi-cylinder, 2-stroke or is mechanical efficiency. Mechanical efficiency in case of this is defined as upon IP. BP is always lower as compared to IP. Supplied is given by mass of fuel multiplied by calorific value, and thermal efficiency is given by W net by Q in. We have two versions of power. One is brake power and one is indicate power. And therefore we have two versions of thermal efficiency. One is called as indicated thermal efficiency, is eta thermal indicated is equals to W net will be IP divided by heat supplied is this quantity. It is called as brake thermal efficiency, represented by eta thermal brake is simply W net will be equals to brake power divided by